Central Valley lowlands, once the rainfall increased and living conditions were favorable. So the animals and plants simply moved up into the mountains. As temperatures and rainfall changed, they came back down to live in the valley. The extreme aridity that I'm talking about probably contributed to the extirpation, that is the local extinction, of macroflora, plants like hickory, wingnut, elm, basswood. All of those disappeared during the Pleistocene in California. And about the same time as the mammoths and the mastodons and the camels and horses and ground sloths. So rather than overchill, it got too cold for them, or overkill, too many of you guys hunting, or hyper-disease, we think you should be looking at hyper-aridity, that is drought, is perhaps not only a, but even a primary cause of the Pleistocene extinctions. It's not a theory that has been talked about widely, but it needs to be. So I thank you for inviting me to make the presentation. I thank Dave Maloney in particular, but other people at Video Resource who've helped with various aspects of the research. And last but not least, I thank you for your attention. And we do have time for questions. And Dr. Green said he'd be happy to answer them.
Where is Maloney?
Maloney's hiding in the back. We'll bring him up.
Correlations with the spores, et cetera, as it relates to like vertebrates or entomology or any kind of between flora and fauna?
It's difficult to use the vertebrates or even the invertebrates in the picture because the temperature and aridity seems to have changed so quickly. In the glacial ice cores in Newfoundland and Antarctica, there are places where temperatures change 10 degrees in 10 years. I think that's really what we're seeing in the Pleistocene. So as a result, we have a calcrete layer that indicates very dry, arid, warm environment, but immediately under it we have mammoths. So it was maybe the cause for the extinction of that mammoth, for that one that died, but we can't correlate either. Our most recent project we had, for instance, immediately under the calcrete layer, 5 juvenile mammoths. Why did all those juveniles die at the same time? There were also a couple adults in there, but it looks like a mass die-off. And it may be because he couldn't make it far enough south. I don't know. Couldn't make it far enough north.
So the calcrete,
Huh?
the subsurface of the calcrete would be an indicator of some kind of like a lacustrine environment?
Most of it fluvial. Very little
Fluvial.
lacustrine.
Very cool talk.
Yeah.
The question I have is, have you looked at oxygen isotopes in these calcretes to do any kind of paleo temperatures? Or is that possible?
It would be possible. And if our clients would pay for it, we would do it. But so far we haven't been able to find somebody that's interested enough to do it. A couple people at USGS have suggested they might want to get involved and do some of the isotopic work. But it needs to be done. Again, this is just a working hypothesis that needs a lot more support, mineralogical and geochronologically, to put the picture together. But I think it's a part of the Pleistocene paleoclimatic picture that we have overlooked. We really have not spent much time looking at drought. And the last 4 years has, I think, brought us around, helped us to think a little better. Dave, did you have a question?
We were working down in Ripon, digging up trenches that were 20, 30 feet deep. And we encountered caliche that were 2 feet thick, not the platy stuff. What's the difference?
There are some, what I prefer
I mean,
to
we hit
call
about 4 of them.
pedogenic caliche, which are thicker and did accumulate in the B and C zone. And those may have formed when temperatures were fluctuating back and forth, rather than just going straight into a hyper-arid event. Because we see some of those caliche also, and we have sampled a lot of them, and as expected, they don't contain any microfossils, because they are deposited down in the B horizon and C horizon, the soil where you wouldn't expect the pollen and spores to be. But the platy ones that were formed right on the surface, they contain abundant microfossils.
So, a couple questions on the calcretes then. As far as wind-blown pollen spores, where would you expect in the glacial or interglacial to be the most predominant wind-blown? In other words, in the arid stuff, would you expect more wind-blown pollen or less? And does that control the population that you're seeing?
We don't see a lot of wind-blown pollen out in the desert today, for instance. But also in cold, wet environments, we don't see a lot of wind pollen.
Okay, so not much.
It's in between those environments where you get a lot more wind, where you do see some distributed. But out of the ones that I've shown you, for instance, it's the oak, the pine, and the juniper that are the biggest wind transported ones. And yet, during the calcrete deposition, those are the ones that are less than 1%. And that 1%, I think, is probably wind blown. But the things that don't blow around are like the algocis and the palm pollen. Those are the ones that are abundant.
And also, so these are fairly impermeable, the clay. So I wonder in where ag is happening, they're running into these things at a really shallow level. Are these preventing in-lieu recharge, what they call it, and, that preventing in-lieu recharge getting down from the surface of the aquifer?
Yep.
Or so is it important then to map these things in the subsurface to see where you do have
It is.
blockage?
The ripping that takes place in the valley is primarily because of those. The soil scientists and the ag people call them durapans.
Right, that's what I've heard.
Durapans, and that's what most of them are, platy caliche, rather than the caliche that's disseminated or nodular. But that's why they have those big D9, D10 cats with one ripper on the back, straining with everything it's got just to break up that platy layer in order to let the roots go beyond it.
Have you ever encountered calyces like you do in West Texas that are several
Once
feet?
again,
The calyces that you encounter in West Texas that are on the surface that are several feet thick?
those are probably more like the platy ones.
But do you encounter that here anywhere in the Central Valley?
No, I have never seen them that, the platy ones that thick.
Thank you.
You alluded to the megafauna extinctions that was the characteristic, talking about the overkill, hyper disease, etc. Is there any kind of existing, I don't want to say consensus, but what's the trend for the explanation currently, if there is one?
I would say at present, it's about 50-50 between overkill and climate change. But when people say climate change, they're really talking about overchill. They're talking about Pleistocene too cold, and that's what killed things off. And I think many of them have missed the point. The point is, it was hyperactivity, hyperaridity. That was droughts, that's how they called it, caused it, not either one of the other two. The overkill may have contributed to it. But let's look at where mammoths survived. Mammoths survived by going north of Siberia into some of the islands. The mammoths survived in California by going to San Bernardino, to the Channel Islands. Those environments, offshore islands, because they're surrounded by cold seas, are naturally cooler and moister. And that's where they survived. Where on land, where it was too dry and probably too warm, they just all died off. So at least it's worth, in my opinion, testing further.
I have one more question.
Yeah.
And that is, what do you think the time lag is between the deposition of the pollen and the deposition of the caliche layer?
I think they're at the same time because many of the caliches are laminated. And those lamina represent seasons or annual deposits, and so you have pollen and deposition taking place continuously during that period of time.
Well, here's what I'm thinking. If the caliche is forming below the surface and the pollen is being deposited not at the same time as the caliche, because it's being deposited on the surface, and subsequently there must be a time lag between these two.
I'm seeing the caliche or calcrete being deposited on the surface at the same time as the pollen is being contributed to the sediment load. So I'm seeing them at the same time.
So you think it's a surface crust?
I do.
Mud cracks? You see mud cracks? You see mud cracks in the caliche?
Yes, we do see some mud cracks.
Oh, you do?
Dave?
Yeah, we sample above and below the caliches also. So we take a sediment sample of the caliche, a sediment sample above it, and a sediment sample below it.
And so the pollen comes from above it as well, not just inside it.
When you're looking at your stratigraphy in the, say, the sidewall, we'll sample the caliche, then we'll sample above it and below it to see if there's a difference.
Is there a difference between pollen?
Above and below, yeah.
One comment and a question. When I worked out in Utah, this was early Cretaceous. Not when I worked out there, but the rock. There were surface caliches that were coating dinosaur bones and palms, so I have no problem with bladey stuff. As you said, driven by evaporation of the surface. The question I have though is going back into the Pleistocene, something that I've never quite understood, so maybe you can explain this, is when you look at the, at least for Western Nevada, the lake histories, going back through stage 3, stage 5, back to, I don't know, maybe 5, or about 100,000 years ago, they're the inverse of glaciers. So when we think glaciers are drying up and pulling all the water into ice, that's when these lakes are filling up. Then during the interglacials, they draw down. I've never quite figured that out. Is that because they're melting as quick as they're growing, or how does that, or I guess put another way, does that fit in with the caliche story that the lakes are during the glacial time and then they dry?
You're asking a question that really we don't have a resolution to. It's very controversial. Some of the people who work on sediments of the alluvial fans in the Central Valley say that these sediments all accumulated during interglacial times. And during glacial times, everything was locked up in ice, and so there was no water flowing out, so there was no sediment being deposited. And other people say, BS, it's entirely glacial deposited sediment. And during interglacials, it was dry and there was no water in the streams. So nobody has an answer for that one yet. But I think the alluvial fans in the Central Valley have a potential for answering some of